Hello. In the last lecture, we looked at the classification of polymers, the first three classifications. Today we shall go to the next one, that is the molecular characteristics, under which we are going to look at molecular weight. So we have seen origin, we have seen thermal response, and we have seen type of polymerization on the basis of which the polymers are classified. Today we shall look at molecular characteristics, out of which molecular weight will be the major focus. So before we go into the characteristics, we should know why we should know the characteristics of a polymer. Understanding the mechanisms by which polymers elastically and plastically deform allows one to alter and control their moduli of elasticity and strength. So knowing what kind of polymer we are dealing with, we can modify their properties or engineer their properties. Also, additives may be incorporated into polymeric materials to modify a host of properties, including strength, abrasion resistance, toughness, thermal stability, stiffness, deteriorability, color, and flammability resistance. The melting temperature of a polymer will influence the manner in which it is processed, as well as the maximum temperature at which it may be used. The physical characteristics of a polymer depends on the first thing that the physical properties will depend on is the chemistry or the repeat unit composition, which we shall deal with, or it shall be explained when the individual fibers will be discussed later on. So we come to the second aspect, that is the molecular weight. Later on we shall also see molecular shape and structure of the molecular chain, how they affect the characteristics of a polymer. Also, we shall go into some molecular configuration and tacticity as the next important reason how the physical characteristics of a polymer are affected. So let us see what is molecular weight. The number of repeat units in a given polymer molecule is known as its chain length or degree of polymerization. So molecular weight of a polymer is the product of the molecular weight of the repeat unit and its degree of polymerization. In short, we can call it dP. So polymers are gigantic molecules and are also referred to as macromolecules. So let us see how to calculate degree of polymerization. Let us take the simple example of polyethylene, which has a molecular weight, say, of 1,50,000 grams per mole. So on the screen now we can see the formula for polyethylene, which has got the repeat unit has got 2 carbon atoms and 4 hydrogen atoms, which are repeated a number of times, shown as N. So the molecular weight of the repeat unit of this polyethylene is 12, which is the atomic weight of carbon multiplied by 2, since there are 2 carbon units, plus 1, which is the atomic weight of hydrogen multiplied by 4. So we get the molecular weight of this repeat unit as 28 grams per mole. So the molecular weight, as we know, is equal to molecular weight of this repeat unit multiplied by number of times it repeats, that is the dP. So therefore, 1,50,000 is equal to 28 grams per mole that we have just calculated multiplied by dP. So dP we get as 5,357 approximately, which is nothing but N. So it means that there are 5,357 repeat units in this particular molecule we are talking about. A polymer sample usually contains a distribution of chains with different degrees of polymerization. So during the polymerization process, not all polymer chains will grow to the same length. So we cannot say that in a particular polymer, all the molecular chains that it consists of will have the same repeat units or the same dP, that is 5,357. So it's a different distribution, and this is decided during the polymerization process. So during the polymerization process, not all polymer chains will grow to the same length. This results in the distribution of chain lengths of molecular weights. Therefore, the above value that we see, 5,357, is only an average value of dp. So how are the degree of polymerization and polymer properties really related? We shall see that. dp determines the physical properties of polymer. For example, the melting or the softening temperature increases with increasing molecular weight, for up to say 1 lakh grams per mole. So, as the molecular weight increases, the melting point also tends to increase. At room temperature, polymers with very short chains have molecular weights of the order of 100 grams per mole, and which will generally exist as a liquid. Those with molecular weights of approximately 1000 grams per mole are waxy solids such as paraffin wax and soft resins. Solid polymers, sometimes termed as high polymers, which are of prime interest here, commonly have molecular weights ranging between 10,000 and several million grams per mole. So we can see as we progress further in the molecular weights, the lowest one, that is 100 grams per mole, will exist in the form of a liquid. If the molecular weight goes higher, it exists in the form of soft resins. And if it goes 10,000 and beyond, it will exist as solid polymers. Thus, the same polymer material can have quite different properties if it is produced with a different molecular weight. Other properties that depend on molecular weight include elastic modulus as well as strength. So, what is the significance of this dp? We can just see the degree of polymerization has a dramatic effect on the mechanical properties of a polymer. As chain length increases, mechanical properties such as ductility, tensile strength, and hardness rise sharply and eventually level off. So this is one say graph which shows degree as the degree of polymerization goes on increasing. One can see that the mechanical properties which is shown by this particular line here, one, it rises up to a certain stage, and then even if the degree of polymerization increases further, it's the graph somewhere flattens. However, in polymer melts, for example, the flow viscosity is shown here in the graph 2 here. The viscosity at a given temperature, whatever given temperature is there, it rises rapidly with increasing dp for all polymers. So at a given temperature, one can, if we were to look at the graph, we see that the viscosity will rise. So as the dp increases, the molecular chain length increases, the viscosity of the polymer will drastically rise. That is, the flow viscosity at a given temperature rises rapidly with increasing dp for all polymers, as shown by the second curve in the diagram. So this diagram gives one a relation between degree of polymerization, the mechanical property shown by 1, and the flow viscosity shown by 2 here. So with this, we come to the end of today's lecture on molecular weight. Thank you.